Thank you for that great introduction. Well, my presentation today is one professor's view of what are the important research topics out there and why I think them important, both from a technical basis as well as a policy basis. So I'm going to tell you a little bit about my general research philosophy up front, and then I'm going to go into policy drivers. It's a bit unusual for a professor to get involved in policy issues, particularly within engineering. But fortunately, I've had that opportunity over the past few years to get involved in a number of policy discussions at the federal level. Then I'll talk about technology drivers. What are some of the real needs within the wireless community, both from a technical basis and also from a policy basis, both commercial and military systems. And of course, for commercial systems right now, what's on everybody's mind, of course, is 5G communication systems, and we'll talk about that. And depending on how much time we have left, I'll talk about some of my current research programs, as well as some ideas that I'm trying to sell to sponsors. So these are ideas that I'm hoping that one of these days we will have a project for, and actively trying to get sponsors for these projects. If you've ever taken a class from me, you know I always bring far too many slides than what I could possibly cover for a particular lecture. And that is true for this seminar as well, but I hope I can get in as much as possible. And I also want to acknowledge the students who have helped to provide some of the materials and that are doing the hard work in my group. Okay, here's my research philosophy. Basically, I'm always looking for the idea that is going to be revolutionary. Not so much incremental, but something that could really change the game. You know, your ultimate goal is to write that paper that everyone mentions in the first paragraph of subsequent papers on the topic. That's your ultimate goal, is to be able to write that paper. So strive for creativity and innovation, but you want to make sure that you're not just doing this research for your own intellectual well-being. You want it to be impactful. So I do try to pay attention to what's going on in industry as well as the regulatory community. And I'm going to start off by talking about policy and also the regulatory community. And as a quick review, there are basically three key regulatory / policy setting bodies. One of them is the FCC, and we're all pretty well familiar with the FCC and how it sets rules. Its scope is limited to managing non-federal spectrum as well as non-federal communications. On the other hand, NTIA, its goal is to look after federally controlled spectrum. And that's a pretty large chunk of the overall electromagnetic spectrum. Many of the radar bands, military communication systems, Park Service, NOAA, NASA, it's covered under NTIA. And then there's the The ITU is an organization that that tries to harmonize communications across international boundaries. So they're the ones who tend to set the prototype for the way that spectrum should be managed, seeking to see consistency around the world. And there's a reason for that. Why do you want the world generally to follow the same sort of standards, the same sort of frequency allocation? Exactly. His response was that you want to create a mass market for the hardware. You want the phones in Europe to be able to work with the phones in the US and in Africa. Because then you have the ability to create these large numbers of devices at a very low cost. And another reason is they just want to deconflict conflicts between countries, conflicts in the use of the spectrum along the borders between countries. So the ITU is a very important body. I thought I'd give you a little bit of background on things that I've done in the past in terms of policy. The first one was serving on the PCAST committee that came up with a new mechanism for how we manage spectrum, using spectrum sharing. And you could think of spectrum sharing as a parallel approach to spectrum management, to unlicensed management, and to licensed management. And roughly speaking, you could think of it as spectrum management like you would manage library books. You can check spectrum out, you can use it, but it can be recalled. And you have a finite duration in which you're allocated to use it. You don't own it, but essentially you're renting it or being loaned that particular spectrum. That's a real departure from the way things have been done in the past, in which companies tantamount owned spectrum. It actually opens up a lot of really interesting business models for the wireless sector. I've also been a consultant on to various organizations such as CTIA, looking at network neutrality, and AT&T, looking at the band plan for the upcoming TV spectrum that's going to be auctioned, as well as their merger. And currently doing some consulting on 5G spectrum as well, in looking at potential regulatory issues with millimeter wave spectrum. I'm also currently serving on the Department of Commerce Spectrum Management Advisory Committee. So I wear a lot of different hats and get to see things from a number of different perspectives. Okay. So let's talk about what's hot in the policy world. What are some of the key things? And how do these things impact the research that we do? Now, clearly, an important aspect of this is spectrum. And lots of things are happening, and will happen this year. At the end of March, we're supposed to have another spectrum auction. How many people have heard about that? No, it's not 10 megahertz. Remember the days in which we had analog TV, and analog TV disappeared because we went to digital TV? You know, one of the reasons why they did that is that they needed to clear up spectrum to support LTE, the fourth generation standard that was coming. And TV spectrum wasn't being used all that much. So what they did is they required them to convert to a digital format, which, by the way, gives you a better picture and is more spectrally efficient. they took those TV stations, they reassigned them frequencies, and then they took the spectrum that was vacated, and this became the first band that we used for LTE. So that is the 4G band, and it's our old TV band. Turns out that countries around the world are doing something very similar to that. Well, we're going to be repacking TV again. You know, they want to squeeze more and more, get more and more spectrum, especially because it produces money. The auction last year for the AWS-3 band generated close to $45 billion for the US Treasury when they sold that at auction. So, politicians love to get money. So, hence, we're going to have another auction, and it's going to be at 600 megahertz, which is good spectrum. And it's going to be different, though. How does it impact us? Well, for one thing, it's a longer wavelength, different propagation characteristics, and it's going to be located right next to TV stations. So, any idea of how powerful a TV station can be? Tens of megawatts of power. And your device may be emitting, on the order of milliwatts of power. So huge power disparities could really drive some very novel approaches to doing RF design because of the dynamic range considerations. You also look at the problem that they're trying to solve. How did they get the TV stations to go along with this? Well, they had what they will be having, what is called a forward and reverse auction. And in one auction, they asked the TV service providers, how much money would it take for you to go away? So we could use your spectrum. And go away might be going out of business or just being carried on cable TV. Okay. And simultaneously they hold another auction. And that auction is to ask the service providers, hey, if we gave you this much spectrum in this particular city, how much would you be willing to pay? So they take the results of those two auctions and they try to play matchmaker. So TV stations will get rewarded for going away. There's a lot of money at stake. People are expecting that some of these TV stations in major metropolitan areas will get many hundreds of millions of dollars to go away or carried on cable. And given that 90% of their viewers are already tuning into cable, that's probably a pretty good deal for them. But just think of this. They have to maintain the same coverage areas for those TV stations that remain, even though that they relocate them. Okay. They have to maintain it, yet they have to change their frequencies, and they will be put in different positions. And you want to be able to maximize the amount of spectrum that you can use for the cellular service providers at the same time. And you have adjacent TV territories as well. And of course, the propagation prediction is sometimes voodoo. It's a little bit of voodoo because you just don't know what you're going to get. You got some good ideas. I mean, you can make some good guesses and you got some tools, but in the end, who knows? So you've got an incredibly difficult optimization problem. One of the big issues that we'll see as well is reassignment of spectrum. One of the the bands that was recently allowed for sharing was a 3.5 gigahertz band, in which you can do spectrum sharing between radar and LTE. There are other bands that are being considered as well, and NTIA is currently studying transitioning the 1.3 gigahertz band. And this is a band that has numerous radar systems in it. It's going to be a lot more challenging than at 3.5 gigahertz. And the propagation characteristics, it will generally signals propagate further distances at lower frequencies, so it'll be one. The other issue, a great research issue, is the compatibility of LTE and Wi-Fi. What is LTE? LTE is an unlicensed version of 4G cellular. And it will operate in the 5 gigahertz band along with Wi-Fi systems. And there seems to be a little war brewing between the Wi-Fi community and the LTE community. There's a concern that the two systems are not compatible with each other. And they start to step on each other's not only spectrum, but their goals as a standard as well. We'll see some new bands enter, particularly at the 5 gigahertz, such as DSRC. I'll talk about that in a while. And then, of course, there's issues in certification and enforcement. As we build these devices that are smart, that can adjust their frequency, that are agile, that are reprogrammable, that may even have reprogrammable policies, how do we manage that? How does the FCC make sure that that doesn't get abused? What keeps a high school student from trying to hack their cell phone and become a push-to-talk device and cause havoc to a cellular network and bring down a good part of maybe a city by doing that? These are scenarios that very well could happen in the future. And of course, network neutrality. I've looked a lot at this issue, and my advice is don't take your spectrum policy advice from late night comedians. If you watch Jon Stewart and such, the issues are a lot more complex than what they appear to be. And the regulations, although in theory they're good in that we're trying to keep a competitive marketplace, the devil is in the detail. And it constitutes regulations that are probably best suited for yesterday's business models and yesterday's technology, not today's technology and future business models. For instance, T-Mobile's getting a lot of flack now for offering free music. It doesn't go against your data charges. So there's lawsuits in progress to keep T-Mobile from doing that. They don't want T-Mobile to be able to differentiate the type of traffic that goes over their network. Some might consider it an unfair advantage to maybe stream Pandora for free, but then this other startup company, well, people have to pay for it. So there are a number of issues there in terms of what will future wireless systems be. Certainly, the ideal network neutrality proponents would say that all bits are created equal in the eyes of their maker. Okay, so voice traffic is equal to video traffic, which is equal to machine-to-machine traffic. But we know in wireless systems, because we have limited bandwidth, that we have to prioritize traffic. And the research here is, as we go to software-defined radios and software-defined networks, and we're trying to optimize across the whole protocol stack, well, we have to consider the zeroth layer, the stack, the political layer. We need to do what we need to do in terms of managing traffic without having to do that. And if all bits are created equal, what's going to be the use of software-defined networks? So LTEU, I mentioned this, lots of potential benefits from this, including being able, for the service provider, being able to maintain a core network that is principally focused on LTE instead of trying to glue together Wi-Fi or other systems that may come along. It's always been a challenge for jointly managing and collaboration between cellular systems and Wi-Fi systems. So if you can make it all cellular, that makes your life easier. But there are issues in terms of coexistence with Wi-Fi. Wi-Fi is a listen before talk type of protocol. And not all the LTEU protocols do that. They manage their use of spectrum, first of all, by trying to find a clear spot, and then secondly, doing a statistical approach to how long should they take over the channel based upon traffic that is currently in the channel. So instead of a listen before talk, almost a deterministic approach, this one is more of a statistical based approach. And not everyone's convinced that that will work. Will it work? I don't know. There needs to be some third-party research done to really shed some light on this. There's multiple forms of LTEU, and you're going to be hearing a lot about this over the coming year. LTEU, it typically will work in a carrier aggregation mode. That is, it's used in conjunction with licensed spectrum, so you can maintain your control channels on the licensed spectrum. And then when you need it, you can use a little bit of this unlicensed spectrum. But the two are tied together as a complete system. LAA is what is being implemented in Europe as their form of spectrum sharing. It is like a database management approach. It depends on licensed spectrum, particularly for control channels. But it incorporates a listen before talk protocol, just like Wi-Fi. So the protocols have some similarity to them. And then there's multi-LTE. This is a new standard. It's not doesn't seem to be a whole lot of information out there. It's being put forth by Qualcomm, and it's a standalone LTE. So it just completely uses unlicensed channels for control channels as well as data channels. These systems are going to have to work with radar systems. And how will they coexist with those radar systems? They'll have to work with other unlicensed systems within those bands. And it's not clear exactly how well it will perform. And of course, there are the drivers of technology, and particularly 5G. 5G is really a hodgepodge of a bunch of different technologies addressing a variety of applications. You can break the 5G applications down into three parts. Those are the ones in the red boxes. Enhanced mobile broadband, okay, faster data rates, sure, we've seen that before. And we'll continue to see it. We want more and more faster downloads. But what is new is massive machine-type communications. The Internet of Things, which I'm sure you've heard a lot about. You know, Cisco's projecting 50 billion devices by 2020 that would be connected to the Internet, and almost all of those devices will be wireless devices. Will they be cellular devices? You know, the cell phone companies want to get a piece of this action too. So they need technology that will address the Internet of Things. They don't want to just give this away to Wi-Fi. And then actually a whole different category of communications to support ultra-reliable and low-latency communications. And applications like that include self-driving cars. Those systems need very low latency. And it represents potentially a huge market. It's been a concept, actually it's been out there a long time, of wireless connectivity to cars. And there's been a system called DSRC, Dedicated Short Range Communication Systems, that was supposed to be the vehicle-to-vehicle infrastructure standard. And it has basically done nothing over more than a 10-year time period. And the reason why they even consider that, and it didn't just go to cellular to begin with, is because of the latency issues. So if 5G can solve its latency issues, then it has this potential for this vast market that will be opening up. The 5 gigahertz band is likely to open up 2 more uni subbands that will have to coexist with radar systems and satellite systems, and understanding their mutual impact is going to be very important. Here's some of the technology drivers for commercial 5G systems. Peak data rates of around 20 gigabits per second. And these numbers, by the way, come from a report that was issued by ITU or 3GPP right at the end of last year. And it's a vision paper for what 5G should be. So these are probably pretty close to what we will see eventually when 5G is standardized. So 20 gigabits per second. For the user, could mean a factor of 10 increase. Spectral efficiency, increase it by 3x. Latency, that one's a real challenge. We have 10 millisecond latency built into LTE now. No way to get around that. There's no fix for it. It needs 5G. We're going to reduce it by an order of magnitude in order to be able to support these new applications such as autonomous vehicles. Okay, so what that means, that means to me, you almost have to throw away what you have and start over from scratch. Because the ramifications are at the physical layer, at the MAC layer, at the protocol layer, the transport layer. It impacts so many different things in order to bring those latency numbers down. And of course, Internet of Things, we're going to need to be able to support more and more of them with energy efficiencies, network energy efficiencies by at least 10x of what we have today. Again, that means some major changes, major architectural changes to wireless systems in order to be able to accommodate that. I also think that accurate positioning is going to be an important research area for 5G to support Internet of Things. Like Professor Bureau likes to call it location of everything. The future is the location of everything, not the Internet of everything or the Internet of Things. So we'll end up seeing higher order modulations, more MIMO, obviously higher frequencies, millimeter waves, new networking technologies such as SDN to support core network functionality, network virtualization, and improved security as well. That one is one that they always say every generation. I've been around the block a lot. I remember 1G, 2G, 3G, and 4G, and now 5G. They never think it all the way through when it comes to security. There's vulnerabilities in all of those systems that eventually they get uncovered. Okay, so how do we stand with 5G? And how does this impact perhaps the timing of research issues? Well, there's a lot of work going on right now in terms of channel modeling for 3GPP, or will be starting very soon. Channel models for up to 100 gigahertz. They still haven't completely developed the scenarios in which they want to run against. They do have the vision paper that outlines some of those scenarios, but the devil is in the detail. And then, this is the way these committees work. They form a committee to talk about when they should meet as a committee. So they are going to hold a meeting in March to approve having a study item. Okay, well, they know that they're going to do it, but you got to have a special meeting for the meeting. And then perhaps by the end of 2019, 2020, we might have more of a complete standard. Frankly, I don't believe it. Things never go as planned, so I would put a couple of more years on that. And typically, it takes a couple of years after the standard is finalized before you start to see the mass deployments. So we're probably talking 2024, if I had to guess, for you to have a 5G phone in your hand for most people. And I could be wrong, and you have probably seen a number of these press releases of companies that say, well, we're going to deploy 5G technology next year. And it's almost like a PR race of how soon can you say that you're going to deploy 5G technology? It's a little bit of a marketing spin. Now, that doesn't mean that elements of 5G will not be deployed. I fully expect that elements of 5G will be deployed between now and 2024. Just makes sense, you know. You try to do engineering in steps, and you try to improve technologies as you go along, especially before you try to integrate technologies. Okay, so for the Department of Defense, their research issues are a bit different, but also, and to a great extent, the same. Spectrum agility, it's always been a military issue. Now it's becoming even more of a commercial issue. And oftentimes we talk about commercial sharing with the federal government, such as the Department of Defense. And I've been in discussions where really the federal government is looking forward to sharing with the commercial sector as well. And that will be interesting to see how that works out. Of course, ad hoc networks are something that the military likes. being able to operate with different waveforms across different networks, and including security domains. This is something that's perhaps not as well appreciated by academics. You have various networks that are supposed to handle certain levels of classification. And can you intermix different types of classification on the same network? Of course, you want your system to be robust to jamming, detection, and kind of the opposite of the commercial sector. You don't want people to be able to geolocate you. Whereas you might want to geolocate, your car keys, but geolocating a military asset, no. And everybody wants low power. What the Department of Defense is facing, though, is that 30 years ago, they used to have the state-of-the-art technology. But these days, Apple has more money than the US government. So you have commercial technologies that are advancing much quicker than the military technologies, and the military is seeking to use these commercial technologies and develop systems that are very targeted to military-type applications. So the technology cycle has to improve for DoD. Okay, let me talk very quickly about some of the ongoing research. And I'm just going to flash through these slides to give you just an idea. And the first one is on spectrum sharing. This is some work that I've been doing with Professor Dietrich on helping to determine metrics for spectrum sharing. How do we know how good a spectrum sharing system is? How do we quantify its performance? How can we quantify the performance, for instance, of the database manager that's supposed to coordinate this spectrum? One that we've been looking for at a while, we just got a new NSF program on, and that is to look at the impact of RF nonlinearities on spectrum sharing. Nonlinearities occur because of strong signals entering the receiver, or at least many times it's due to strong signals entering the receiver. And when you have an ad hoc use of spectrum, you end up in situations where you may have a very strong adjacent channel interfering signal. Before, when the FCC did band planning, they were able to mitigate those types of problems. But if it becomes much more ad hoc, then your radio has to mitigate these issues. Some of it is a matter of how you assign frequencies to different users and matching those users up with the quality of their receiver when you do a channel allocation. Nonlinearities will cause co-channel interference. And are there things that we can do, perhaps, to come up with the equivalent of an information theoretic that includes the impact of nonlinearities within our capacity calculations? Okay. One of the, actually, several of the programs that we've had are looking at how we do spectrum management through this database type of approach. How can we protect the legacy users of the spectrum, who are there, they have the first rights, the legacy users, while being able to maximize the capacity of the new users or the secondary users. The secondary users cannot interfere with the primary users. And of course, one way to do that is to create an exclusion zone, which you keep these new users from operating in. But yeah, that could really lead to a very inefficient allocation of spectrum. You probably will have to exclude much more area than what you would really like to do. So how can we come up with better ways of defining these exclusion zones and ensure that we minimize the interference to these legacy users? Furthermore, there are security and privacy issues with this. Okay. I mentioned the 3.5 gigahertz band is one band that has been transitioned to spectrum sharing. It's also a band in which you have military radar systems operate on ships. So when they get close to the coast, well, then the users have to turn off. How do they turn off? You recognize that there are ships with radars out there, and you inform the database, and you turn off all of the users using those frequencies within that region. Of course, that is a potential security problem. As if you wanted to figure out where those military ships were, you just go to the database, and you look at what frequencies have been excluded. And that tells you a lot about the position of those ships, as well as activities on government satellites as well. So there's information that can be inferred by looking at these databases. So you have to come up with approaches that provide some sort of assurance to the legacy users that their information is being held privately. Another thing that we're thinking about, this is actually looking for a sponsor on it, and that is carrier aggregation of ad hoc systems, being able to use multiple bands simultaneously as a complete overall network. And that's a property that we've seen in LTE, in the latest releases of LTE as carrier aggregation. And this is one that the carriers just love because they think of the spectrum now as just this big blob that they can have access to. They can coordinate it. You don't have to have separate coordinations for different spectrum. You coordinate it all together as one entity. Gives you better spectral efficiency and more reliability. If you could cooperate between the primary users and the secondary users, you might be able to improve the overall efficiency. For instance, instead of completely keeping a secondary user out of a particular region that a primary user might use, give the secondary user a probability that you might be using that band within a certain period of time. And use that metric to help determine where the channel assignment should be. So you don't give away anything specific, you just give away probabilities. For DoD, they're looking to understand how they can protect their rights in this era of spectrum sharing. For instance, remember that AWS-3 band that I talked about that sold for $45 billion? That band is actually a shared band. And it has to be shared with existing military systems that are too expensive to buy new equipment for. And in general, those are airborne systems. So how do you first of all, how do you tell the carriers that they can or cannot use the spectrum that they just spent $45 billion for? And particularly, some of the early exclusion zones were huge, taking out major metropolitan areas that were essentially worth hundreds of millions of dollars in terms of their value of spectrum for an occasional military flight. So you have to allow for some give and take. But from a DoD perspective, you also have to make sure that your systems don't get interfered with. So you need methodologies for determining when a violation does occur. Unmanned aerial systems, we've done a little bit of preliminary work on this. UASs are all the rage now. If you can spell UAS, you've got a job in UAS systems. For the military, they have dedicated spectrum for UASs. For the commercial world, there is no dedicated spectrum for UASs. You know how these commercial unmanned aerial vehicles are communicating? Any guesses? ISM band. The ISM band. That, obviously, you don't get any protection in the ISM band. That and what does your interference environment look like? Let's say that you've got a UAS that's up here and you're looking at the Earth. Can you imagine what the interference environment would look like? Now you have a view shed of a much larger area with a lot more Wi-Fi devices or whatever else is in those ISM bands. So the interference issues become very, very hard to get around, particularly if you're trying to download a 4K video link. So how do we solve that? Well, that's a good thing for you to figure out. Speculation is that it will be done with spectrum sharing. But if we do it with spectrum sharing, and we've done spectrum sharing, but we've assumed that the base station stays still. Now we're assuming that essentially you've got these emitters that are roaming around large areas, radiating big areas. How are you going to deal with that? Really opens up the possibilities for new ways of spectrum sharing in order to be able to handle this problem. Oops. Okay, so LTE. Oh shoot. I'll try to hurry this up. One of the things that we've done in the lab is we've looked at the vulnerabilities of LTE. As I mentioned earlier, every standard has its flaws, its security flaws or information assurance flaws. And LTE certainly has that. There are issues with the control channels with LTE, and actually some issues that were caused by either inconsistencies or vagueness within the 3G or 4G standard. So we've examined various vulnerabilities of LTE, and hopefully some of the ideas that we've come up with will end up in future standards. Some of the fixes are actually pretty easy. Here's one we're looking for, actually for a sponsor for, and that is wargaming with LTE. There's a lot of new LTE systems that will be coming up in what we call a greenfield deployment. It's the first deployment of cellular in this particular band. And it generally takes about a month for the carriers to bring up a cell site, a macro cell site. They end up doing drive testing and network parameter optimization. In that time, are there things that we could do as academics to come up with scenarios for how that LTE system might be able to respond in an emergency situation? Like with Hurricane Rita a number of years back. I was in Dallas when that happened, and it threatened Houston. So what did they do? They converted all of the highways that go out of Houston into one-way roads. And it was still bumper to bumper to get the people out. Now, what do you think that did to the cellular network? You probably couldn't make a phone call, would be my guess. Signal processing and resource management. This is some of the work that Matt Carrick has done. One of the things that will probably happen with 5G is it will probably have a new physical layer, something other than OFDM or something that's going to be a modification of OFDM. One of the reasons is the ability to deal with adjacent channel interference. OFDM is not very good at handling adjacent channel interference. And actually at AWS-3, you've got a big military system right in the middle of the LTE band. One of the approaches that has been recommended is just turn off the subcarriers in that band. But LTE doesn't really have that good of side lobe rejection. LTE is basically a bunch of filtered signals, filtered communication signals that are stacked right next to each other, and they're not filtered very, very well. So coming up with techniques that are more robust to interference and can do improvements in spectral efficiency as well as reduce latency. This is a potential waveform that can reduce latency. Latency and reliability go hand in hand with each other. The normal way that we deal with an error is that we ask for a retransmit, and a retransmit just kills latency. So if you make it more reliable, then you don't have to worry about retransmissions. We've also started some work in looking at self-interference cancellation. Caleb has been doing some of this work of being able to transmit and receive on the same frequency at the same time. It sounds like a really difficult task given that you're trying to measure powers and microwatts and transmit at hundreds of milliwatts. But it has been shown in some cases to be able to work. Ultra low latency communications is a very wide open area for research. One that I haven't seen a whole lot of literature on to this day, particularly from the wireless perspective. Non-line of sight millimeter wave communications. There are really nice things about millimeter waves. It's considered one of the leading features of 5G. Very, very high frequencies, 28 gigahertz and above. But those signals propagate like light. They're easily blocked. They tend to scatter too when they hit a surface. Are there ways, I know this sounds almost impossible, are there ways to have non-line of sight millimeter wave communications? And we think there are, by borrowing some principles from the radar world, radar effects, such as ionization trails. Plain ionization trails allow you to reflect radar signals. Can we design mechanisms for ionizing portions of the atmosphere to allow for a millimeter wave link to reflect off of? Or radar chafe. You know, if you watch the Top Gun movies, when they're being hit by a radar, what do? They release the chafe, right? Which is like this foil that confuses the radar. They're getting reflections off those millimeter wave systems. So are there things like that we could do to give some non-line of sight capability to millimeter waves? That's when we're talking with DARPA about. And of course, scheduling multi-user MIMO systems, grouping users together because we have limited antenna resources, and then combining that with scheduling and channel state information. And green communications. This is one that Meow's working on. And can we use scheduling? Can we reduce the peak to average ratio of the signals to reduce the demands on the power amplifier. We want to be able to use power amplifiers that are more efficient, and they're more efficient because they don't have to contend with the peak to average envelope variations of the signals. And another one in wireless distributed computing. This is based upon some DARPA work that we did. And the basic idea of this one is you shouldn't have an IC. Any IC should not have pins. There should be no pins in the IC at all. And why? Pins are a point of failure for the IC. You know, they come unglued from the socket, all sorts of issues with reliability and manufacturing cost as well. So why not use wireless power in millimeter waves for those chips to be powered and communicate by? So that's basically it. It's an idea of current and hopefully future projects. Any questions? Any comments? Now's the time to throw those rotten tomatoes.
So I have a question.
Sure.
You had some discussion on low latency communication.
Yes.
And you said that it basically needs a completely sort of new network in a way, because your network backbone is not really going to be reused for that. So what are your thoughts about that? So where is this current cellular network going to go? Is it going to, are we going to partition the services, which are more sort of delay tolerant, which will then be routed through the older network, and then there are newer applications which require tighter latencies that will be routed over the new network. So any thoughts on that?
Yeah, I think that's where software-defined networking can play a great role in helping to set the prioritization of that. But by the way, that goes against network neutrality, at least network neutrality by the purist. But, you know,
that's what
we have to.
So
we're practical engineers.
I
know, but for those who are not in the area, it just seems just right that all bits are created equal in the eyes of their maker. But we know that's not true. And of course, the FCC says, yeah, we'll give you some network exception, but how do you define a network exception? So I think there are a lot of challenges, and software-defined networking has great promise to help reduce those latencies. It also, though, means, I think, revisiting the physical layer. We can't have retransmissions. We just can't. So we have to make it much more reliable. We have to have a more reliable physical layer. We can't afford much processing in the physical layer. You know, one of the things that we tried to do was a digital repeater for LTE, and we ran into problems because of the FPGA introducing too much latency into the system for the feedback. So it requires very careful formulation of how you do the demodulation, how you do the MAC, and how you do the implementation in order to make that. So it's a really hard problem. I think it's the hardest problem in realizing 5G.